Hello, everybody. My name is Lutz Jaitner. I'm from Germany. I entered the field by 2006. I want to thank you for the invitation to speak here. I became interested in the puzzle of LENR, and I wanted to solve it, but it took me a long time. So my goal was I wanted to have an explanation that remediates LENR, L-E-N-R, with the established principles of physics. And that turned out to be a hard journey. But I believe I achieved something that fits into that picture. So the puzzle, as it was apparent to me, consisted of some input elements that went into a reaction and produced results which seemed to be at odds with established principles of physics. So, as was said already here, there was an observation of helium, which could come from alpha particles. There are some protons emitted, not many. There is an output of stable elements instead of radioactive isotopes. So especially the absence of tritium was one puzzle piece that didn't fit well. There is heat output and there is X-ray output, but no gamma. Very few neutrons were detected. The cathodes sometimes showed very interesting craters that could not be so easily explained. And lately, there is an increasing number of observations of strange radiation. I will dive into this. I will explain what it is or what we see in the experiments. And this was also something that didn't fit in the traditional picture. And on top of that, there are some radio frequency emissions. There are some very interesting magnetic effects. So all this contributes to a puzzle that I wanted to solve. And I looked at the current explanations that exist in the community, and I was asking myself, could it be the lattice? Is it plausible that the lattice is conducting this reaction? And I was analyzing massive amounts of documents that already were produced by the experimentalists, and I didn't find a very strong evidence that the reaction really occurs in the lattice, because then the reaction products would have to show up in the lattice. I couldn't find much of an evidence either that the increase of the surface of the material will proportionally increase the reaction rates. So I tried to put something else in there as the intermediate state or the nuclear active environment of LENR. And I named it Condensed Plasmoids, which is the title of this presentation. So my approach is I want to compute with quantum mechanics a intermediate state with a much higher electron density than in normal matter to explain the reaction. So let's speak about strange radiation. I believe that strange radiation is the same as condensed plasmoids. So what you see in some of the experiments is exactly this intermediate state. The strange radiation or condensed plasmoids have been seen many, many times and were named in many different names by experimentalists, such as Winston Bostick. He called them vortex filaments or current filaments. Ken Shoulders had observed them and named them EVs or EVOs. Then there was Takaki Matsumoto. He named that ring clusters or something like that. And there was observations from Savatimova and Rodionov. There was observations from Urutskov. I think he named that strange radiation. So that's where I got the name from it. And then there were more recent photographs from Claude Davio and co-workers. There are other terms in use, let's say micro-ball lightnings and so forth. So it has been seen over a very long time, and nobody could explain what it is. So let's look how they appear in experiments. What can be seen there? One of the first photos in the LENR research was from Mosier Boss and co-workers at SPAWAR, and they appear to be little craters that looked like molten palladium in otherwise not molten surface. And they were called micro-explosions because the assumption was that some very high thermal energy caused this melting. I do not believe it's melting. I do not believe the effect is thermal, but what you see is a crater. Now, other experimentalists have seen other craters. For example, Ken Shoulders, with very little energy, was able to create little objects that hit surfaces and created craters, which again looked like molten. Then there were electrolysis experiments in the Fleischmann-Pons type electrolysis. They produced a sort of crater that was not molten, but interesting enough and compares to what the other pictures show. Excuse me. There are other forms of these objects, so they do not always look the same. So Ken Shoulders saw this ring structure in one of his targets, which made him very curious about the nature of these objects. Matsumoto saw these ring clusters, very many of them, in electrolysis experiments. Then there was a photograph on X-ray film, I believe, from Claude Daviau, which is a very clear picture, very nice ring. There was a similar photo also on X-ray film from Rodinov and Savatimova. So this is another example of what can happen. And strange enough, in some cases, we see periodic or quasi-periodic structures of very different flavors, many types of them. And in my model, which I'm going to explain, there is a basic structure, a self-organized structure of these objects, which can be used, if you deform that slightly, which can be used to explain these complicated patterns. So this is one indication that the explanation I have and the experiment, the microscopic images in these experiments show the same thing. Now let's explain what the basic idea of my theory is, because I believe this is easy to understand and everybody can kind of think about it. Excuse me, what was that? This equation shows the strength of the magnetic field at the surface of a wire where a current flows through. So nothing special, usual textbook formula. The interesting thing is that the radius of the wire is in the denominator, which means there is a singularity if that radius approaches 0. Now let's think through what that means. It means if you have a wire, and let's assume the wire is not a piece of metal. Let's assume this is a plasma, right? A current-carrying plasma is a plasmoid, so it's a plasma wire or a plasmoid that is having this radius. Let's assume that. Now, if the magnetic field increases, what will happen? It will create a pressure on this plasma. It's a pinch effect, a set pinch, and the wire will become thinner. Now, this formula says if the wire becomes thinner, then also the magnetic field becomes stronger, and this is kind of a positive feedback. Once you have a critical value of current over magnetic field strength, then this goes, so to speak, forever. It will collapse the matter in something very dense. And the interesting question is, how dense will that become? Where does it stop? So there are two answers to that. The first answer is the compression that takes place in the Z-pinch will normally increase the temperature to a degree that you have thermal pressure, and the thermal pressure will create some instabilities or will hinder the further collapse of the matter. However, there is also radiation coming out of electromagnetic radiation, which cools the plasma. And if that is a very thin plasma wire, the cooling is very effective. So let's assume the temperature is low and will not produce the back pressure. Then what will happen? What will stop the collapse? And the answer is it's the degeneracy pressure of the electron gas. It's a quantum mechanical effect. You can't compress electrons in an infinitely small volume because it would increase the kinetic energy. So this is what I wanted to calculate. The quantum limit of the compression that takes place in a Z-pinch. Now this is the result of a plausibility check. I wanted to assure that my calculation results were in sync with basic formulas known in physics. So I was using a formula that's popular in astrophysics to compute the degeneracy pressure in white dwarfs, which hinders the collapse towards a neutron star. So that curve is this one. I computed the magnetic pressure from my simulation results, and they were not far apart. So it roughly looks like I did a reasonable job somehow to compute the right pressures and forces in there. Now, astonishingly, the pressure that comes out here is 2 times 10 to the 21 Pascal. This is 5 orders of magnitude higher than the pressure in the solar core. So we're talking about something very exotic here. And this is just a Z-pinch collapsing to something else, to the quantum limit. The results you see here in these curves were obtained at a radius value of 35 picometers and a current, intrinsic current in that wire of 9.2 kiloamps. Let's ask the question, which physics applies to these objects? We have a choice between plasma physics to describe that because it's a plasma or a plasmoid. We have a quantum mechanics, which may be good because we are collapsing towards the quantum limit. Let's see what it says. If we have plasma physics at low temperatures and high densities, what does it give? Plasma physics would predict that the plasmoids dissolves into atoms and molecules. Well, that makes no sense. At these densities, there cannot be atoms anymore because they are much too close to each other. The electrons become delocalized, so you won't see atoms. And also, the current does not stop. This whole thing is still conductive even at low temperature. So I would think that plasma physics is not aligned with the observed lifetimes of these objects. The plasmoids do not decay into regular atoms and molecules as far as the experimental results show. So what I thought that I need quantum mechanics. And to be honest, I hate quantum mechanics, but I had to use it, right? And the quantum mechanics predicts that the condensed plasmoids remain in the plasma state because of delocalization of the electrons, and only this aligns it with the observed lifetimes of condensed plasmoids, which go up above hours and in some cases even days, what has been seen in the experiments. The next slide shows the basic assumptions I'm putting into my quantum mechanical modeling, because I wanted to know the properties, so I had to do some computation, and for the computation I need a model. So the model does very few assumptions. It assumes that we have a long channel, a plasma wire, with densely packed nuclei. It assumes that the distance between the nuclei are so small that all electrons are delocalized along this channel. And the electrons are supposed to move relatively to the nuclei so that I get a current through that plasma wire. So this is all. This is the whole set of assumptions. Nothing else. No rocket science. I'm using something that is hopefully well established in the textbooks. It's the Hamiltonian with so-called minimal coupling. It describes the total energy of an electron in a magnetic potential and an electric potential. So it should be familiar and it should be agreeable. The formula is a relativistic one because I assume or I will get out velocities of the electron which can be up to 80% of the speed of light, and I thought it's more precise to do a relativistic Hamiltonian. If you quantize this Hamiltonian into a quantum mechanical equation, you can come up with the Klein-Gordon equation if you ignore the electron spins. It's kind of the direct way to quantize the Hamiltonian. So I did this, and I was using cylindrical coordinates because I have a long plasma wire. It has a cylindrical symmetry in it. Then I needed to compute the electrical potential and the magnetic potential from the wave functions and the nucleic charges. So this is the formulas that was put in for that purpose. And then I had to solve this Klein-Gordon equation. And in order to do so, I first of all made this product ansatz. So I wanted to separate the wave function into something that is going in axial direction, in azimuthal direction, and in radial direction. And the actual wave function solution is known, so that I can write that down. It's done. The azimuthal wave function is also known. It's done. Only the radial wave function looks a little bit more complicated. It's the solution of this component of the Klein-Gordon equation, which I have to solve. And unfortunately, there is no analytical solution available in the literature for that differential equation. So what I did was I was replacing, or I was doing an ansatz where the wave function was approximated. This is the radial wave function here. It was approximated by a polynomial multiplied by a radially decaying exponential function. And also the potentials in my equation was approximated by a polynomial. So if I put that into my differential equation, I can find an analytical solution. If I use these coefficients for the polynomial here, I have an analytical solution, which is nice because it speeds up the computation time. I need to say something else here. I need to say that, just a second. With this equation here, it is assuming that I can, with reasonable precision, use a single electron wave function computed from the mean potential of all the other electrons and the nuclei. So this is an approximation again. It is not the full quantum mechanical solution that you would normally do, but I have billions of electrons. I need to be more simple in my approach. So, what comes out of that simulation? So I wrote a program, I simulated thousands of orbitals. Each of the orbitals represent large groups of electrons. And the summary of that, what comes out, the parameters that I computed is, I found no upper limit of these objects. They can grow infinitely large. I found something that is somewhat a minimum length. So these objects seem to have a minimum length in the order of 10 micrometers. It's not precise, it's just a guess, so to speak. I see in the electron distribution, I have a radius of these plasma wires which go in the range of 35 to 130 picometers, and it's a range because the condensed plasmoids can exist in many different configurations. The matter density in these objects can be up to 100,000 times denser than ordinary matter. So this is very significantly different from what people tried in a lattice, right? It's much higher density matter. There is an intrinsic current flowing in these objects. The current cannot stop. If the current stops, the force goes away that compresses the channel, and the whole thing explodes. There are reasons why these currents continue to flow once they have been started through external conditions. The mean velocity of the electrons is between 16 and 40% of the speed of light, and the potential inside the core of these objects goes between -7 and -60 kilovolt. The reason for that is there is an excess of negative charge in there. So there is, let's say, up to 2% more electrons in these objects than nucleic charges, which make them attractive for the ions. The ions are safely trapped in there, but the electrons are not. They could fly out, and only the magnetic field holds them towards the core. Of course, I wanted to know also the binding energy, and that came out as a disappointment. The binding energy is between 10 and 120 kiloelectron volts per electron. So this is an endothermic binding energy. From an energetic perspective, it's an unbound electron, but it's not unbound in the sense that it will fly away. It's unbound in the sense that if you stop the movement of the electrons, it will then fly away. So I believe that this is a preliminary result. I believe that I have some terms missing in my Hamiltonian, which will in later time find a correction. I can't tell you now, I don't know. Let's look at the electron density distribution. So you see these curves here. This one is the electron density, and the other one is the current density. We have 0.2 electrons per cubic picometer, which is extremely high electron density. We have current densities of up to 2.8 amps per square picometer. This is astronomical high densities. From that, we can compute, or I could compute, the electric field, which goes up to plus minus 700 volts per picometer. We have magnetic fields which go up to 50 megatesla. This compares to the magnetic field in a pulsar, right? Astronomical objects, pulsar. So it's something that you cannot achieve in the laboratory on a macroscopic scale, but microscopically the fields are that high. So once you accept this result from the simulation, then you can ask the question, what does it enable? How does it relate to the LENR experiments? And a key thing to translate that to experimental findings is the minimum distance between the nuclei that comes out of the calculation. And it's 2 picometers with hydrogen, 4 with oxygen, and 8 with gadolinium, for example. This is small enough, I believe, to enable tunneling through the Coulomb barrier. And the Coulomb barrier is also very much shielded by the high electron density. So we have much more likelihood for Coulomb tunneling. And it also works with other elements. So here with gadolinium, which is a relatively large atom, you see this is still so close it can tunnel. So we would expect tunneling not only with hydrogen, but with all sorts of elements. Also, this is really cold fusion. The elements do not need to have kinetic energy to do the fusion, because it's purely tunneling. And the nice thing is they stay next to each other for very long times, so there is enough time. When that tunneling happens, some of the energy of the excited elements can cause spallation. So if we do not reduce ourselves to just fusion, but assume also the potential output channels, we can see fusion fission as an option. So this is just a hypothesis, but I think it explains why elements like helium, like calcium, like iron will be produced with something like deuterium and palladium, for example. So you wouldn't expect that from a simple fusion process, right? I came up with yet another hypothesis that the high electron density is also helping to carry away the nuclear excitation energy. So if the nuclei are excited and vibrate or oscillate in the, with their electric and magnetic dipoles, the high electron density and the high current density could absorb that energy and convert it down to small changes of the electron velocities. So it's a process of down conversion. I have to hurry up a little bit, well, because the time goes by.
Keep time for questions because you are going to get dozens of questions.
Yeah, sure. I'm happy with that. So yet another assumption is, or hypothesis is, that the high electron density is able to enhance beta plus decay, or would enhance electron capture in favor of beta plus decay, which would explain why we don't see the annihilation radiation coming out of positrons. So, what we see in experiments is that these objects stay for a long time. I think there is a nuclear feedback into the kinetic energy of the electrons. So I believe that the cooling of the nuclei by the electrons lead to an increase in the velocity, in the average velocity of the electrons, which would explain that these objects can grow and can produce electricity to the outside electrodes. This is one of the most interesting speculations in there. I would say be careful with these objects. I have seen many experiments in the past where people did not even know that strange radiation exists. I believe these objects are dangerous to the human body. It is known that they can produce intense X-ray and ultraviolet light. This is not a speculation, this is a known fact. Observers, experimentalists, have seen them passing through thick walls of LENR apparatuses, so they come out of your apparatus unexpectedly. They can destroy electronic components easily. They can ionize all matter, which often looks like melting. You have seen that in the craters that I was showing you. And I would advise, and this is really, I mean, I hope you stay healthy for your entire life, and I think it requires proper shielding of your apparatuses. I would recommend thick walls of iron before we know a better solution to that. I have one more slide because
please keep calm.
A warning is not a good end of a presentation. This slide shows an apparatus from Anatoly Klimov. Thank you, Anatoly, for this excellent experiment. I will not explain the details of that. I will only focus on the cathode here, which has a very wide shining here. And when yes, and the cathodes afterwards show these cratering in their surfaces. So the comment that I want to make is, you can see condensed plasmoids with your naked eyes if they have a high density. Anatoly calls them erosive metal clusters. It doesn't matter, it's just another name for the same thing. And I tell you, once you see them glowing in this way, and once you see the craters here, you do no longer need to have calorimetry to find out whether you have excess heat. You will have excess heat in the kilowatt range. So the real challenge now is build an apparatus like Anatoly did, which shows this glowing, and we are almost done. Thank you.
So thank you again. I guess we have so many questions that I propose that people who do want to discuss that with you, don't drink coffee, keep here in the room during the coffee break, you know, because there are probably so many questions. I have even an urgent one myself, because, you know, the instability you show in plasma, it reminds me that in the 15s already, the physicists working on hot fusion made a zeta pinch experiment, you know, and they discovered the first instability in plasma, the sausage type instability, exactly for the reason you mentioned. But at that time they were making hot fusion, and they did see neutrons.
In plasma focus devices, they saw filamentary structures which are identical to condensed plasmoids, so they also saw cold fusion. You're right.
Yes, but in that case you get neutrons. We don't see neutrons. So,
a question, I understand the generation of these things, or more or less in a plasma focus experiment and similar experiments. But what does that have to do with, let's say, outgassing from palladium cathode? How do you account for the generation of these things in an experiment that seems to have a very low energy density? Where is the currents coming, and how can you think about that?
I do have a reinterpretation of the Fleischmann-Pons experiments. Please come to my poster paper and I will explain in detail how that works. I can't say it in one sentence, sorry.
No, okay. Again, I guess we should keep on time. I prefer we stop here, and again, the people who want to discuss this are invited to stay in the room during the coffee break to have a continued discussion if you agree.
And
you don't need a coffee?
Yeah, I'm happy with your solution.
So it depends if you prefer theory of coffee, you make your choice. For the coffee break. For me, I stay in this room.
Lutz, it's absolutely fantastic that this science gets an airing at this conference, so thank you very much for your contribution. First, strange radiation can be misinterpreted three-body interactions, and just like spots and worms can sometimes be misconstrued as muons, we need to be able to separate that. Now, Bogdanovich has done a lot of work and showed that condensed plasmoids can survive for 2 days. The military have come to me and said that they've seen them for 2 months transmuting matter. So these are real things, and they can also form crystal clusters that can then go over a surface and cause similar tracks. So you need to look at systems like, for instance, in a webcam, or what I saw with the EcoFuel, where the plasmoids absolutely shredded plastic that wasn't moving at all over a number of days. Savatomova saw these things, I think, and other researchers have seen their LENR material change elements over a period of time. And I think, you know, that's because of these structures. Then the subject of how it's happening.
Sorry. If it's that long, you know,
Okay.
we have to keep